Welcome back to Very Ordinary Differential Equations. In this lecture, we complete our study of linear first-order systems of equations with constant coefficients by incorporating the study of complex eigenvalues. In solving the system y prime equals ay, where we have an n by n matrix of constants, we know that what we need to do is find a fundamental set of solutions. The eigenvalues have algebraic multiplicities that add to n. But the characteristic polynomial might have an irreducible quadratic factor, something of the form lambda minus alpha squared plus beta squared, which corresponds to roots of the form alpha plus or minus beta times I. When factored over the complex numbers, however, everything works just like we've been doing. If alpha plus beta I is a complex eigenvalue with eigenvector u plus vi, well then, a of u plus vi equals alpha plus beta I u plus vi. A of vector equals eigenvalue times vector. This is exactly the same thing, we're just throwing complex numbers into the mix. Now, given that the system of equations began with all real coefficients, it might not be desirable to express solutions in terms of complex numbers. If, by the way, you are fine presenting solutions in terms of complex numbers, then you're already done. Nothing changes from all the work we've done before. If, however, you want to be able to backwards convert this into the real numbers rather than having any apparent complex numbers floating around, there's some work you can do. Complex roots necessarily come in conjugate pairs, alpha plus or minus beta I. And since a of u plus vi was alpha plus beta I u plus vi, if you apply complex conjugation to both sides, noting that the matrix A has all real numbers and therefore is its own conjugate, you get a times u minus vi equals alpha minus beta I times u minus vi. That's to say, if you have a complex eigenvector with a complex eigenvalue, then the conjugate of the eigenvector corresponds to the conjugate of the eigenvalue. So if you can find an eigenvector for one complex root, you've really already found an eigenvector for its complex conjugate. You just need to conjugate your eigenvector. So what we have is a pair of complex conjugate eigenvectors corresponding to a pair of complex conjugate eigenvalues. Using all the techniques we already know, we can find solutions of the form eigenvector e to the eigenvalue t. Also, we know if this eigenvector corresponds to this eigenvalue, then the conjugate of this eigenvector corresponds to the conjugate of this eigenvalue. Applying Euler's formula, notice that e to the alpha plus beta it, I can factor e to the alpha t out, leaving behind e to the beta it, which by Euler's formula is the cosine of beta t plus I sine of beta t. F2, if I apply the same work, would give me u minus vi e to the alpha t cosine beta t minus I sine beta t. These are complex valued functions, and the goal is to convert these into two linearly independent real valued functions. So what we're going to do is come up with a clever combination of f1 and f2 that produce real valued functions which are linearly independent. So here was f1, expanded all the way out, where now we're taking u plus vi and multiplying it across this whole thing. U and v are vectors, but we do still have this I here. So for example, vi times I sine of beta t is going to give me this negative v sine of beta t. So we collect the real terms here and the imaginary terms here. F2, we're going to do the same thing, expand out that u minus vi and collect real terms versus imaginary terms. So now we have f1 and f2 fully expanded out. 1/2 f1 plus f2. Now when I add f1 plus f2, notice that here I have I times v cosine beta t u sine beta t, and here I have negative I, the same thing. So the imaginary parts cancel out. When I add them together, I just get 2 times the real parts, which add up quite nicely, but I multiplied by 1/2 here. So overall, 1/2 f1 plus f2 is just e to the alpha t u cosine beta t minus v sine of beta t. And similarly, 1/2i times the difference is e to the alpha t v cosine beta t plus u sine beta t. All in all, if alpha plus beta I are two complex conjugate eigenvalues with corresponding eigenvectors u plus or minus vi, then two real valued solutions are given by e to the alpha t times u cosine beta t minus v sine beta t, and e to the alpha t v cosine beta t plus u sine beta t. This is just a handy thing to remember where it is so you can look it up when you need it. Now, what if there are deficient complex eigenvalues? This is pretty much never going to happen in a problem that you're expected to work out more or less by hand under time constraints, but in theory, you might have deficient complex eigenvalues. The same techniques apply. Starting from an eigenvector, which is now a complex eigenvector, u plus vi, construct a backwards generated Jordan chain, etc., etc. All the same stuff works. You can convert them into real solutions if you want, using similar techniques to what we just did here. But since they pretty much never come up in an introductory course, I'm not going to go through the details here. Okay? If we have complex conjugate eigenvalues, they're not going to be deficient, because this is an introductory course and we're not that cruel. So here's our first example. Find the general solution to this system of equations. Well, we start off the same way we're used to doing. We find eigenvalues. So we set up the characteristic polynomial and set it equal to 0. Here is lambda subtracted from the diagonals, and there's the determinant computed. So we need to solve for 3 minus lambda squared plus 4 being 0. And we quickly see there are two complex conjugate roots, 3 plus or minus 2i. Now for the eigenvalue 3 plus 2i, we're going to find an eigenvector. We don't need to find an eigenvector for the other root, 3 minus 2i. Once we find an eigenvector for 3 plus 2i, its complex conjugate will automatically be an eigenvector for the complex conjugate root of 3 minus 2i. So we only have to do this once, thankfully. But we set up a times v equals lambda times v. There's the matrix A. There are unknown coefficients a and b. Lambda is the complex number 3 plus 2i. Observe, a and b are presumably complex valued numbers. They're not just real numbers now. So here's the system that we now need to solve for a and b. In the top row and in the second row, we get the corresponding equations. Notice in the top row, if you distribute out this 3, you exactly get a 3a, which cancels this one. Pushing the 4b to the other side, you get 2ia plus 4b equals 0. Now, if I divide every term by 2a, I get a. 4 over 2 is just 2, and 1 over I is equivalent to negative I. So dividing by 2i turns this into negative 2ib. The two equations are now seen to be scalar multiples of one another. If you multiply the bottom equation here by 2i, you'll end up with the top one once you distribute everything out. So the only equation we have to solve is a minus 2ib is equal to 0. In other words, a is 2i times b. So let's just go ahead and let b equals 1. Therefore, a is 2i. So we have an eigenvector now of 2i, 1. For real valued solutions, we want to express it in the form u plus vi. We want to separate this eigenvector into its real and imaginary parts. So we simply write it as 0, 1 plus 2, 0 times I. So in this formulation of u plus vi, u is the vector 0, 1, and v is the vector 2, 0. Now that we have a complex eigenvalue, 3 plus 2i, so alpha is 3 and beta is 2, and we have u plus vi, where u is the column 0, 1, and v is the column 2, 0, we have a formula that we can just refer to generate our two solutions. So here were our two vectors. They corresponded to the eigenvalue 3 plus 2i, so if I apply all of that information to the earlier formula, our solutions are of the form e to the alpha t u cosine beta t minus v sine beta t, which corresponds to, well, alpha is 3, so we get e to the 3t, u was 0, 1, there it is, and beta is 2. So I stick that in there, I fill all that in, and I collect it as a nice simplified column here. y2 is e to the alpha t v cosine beta t plus u sine beta t, which collects into a nice column there. And our general solution is now just c1y1 plus c2y2, where y1 and y2 are these columns right there. So not so bad. For our second problem, let's solve an initial value problem. Y prime is the given system, and y of 0 is the given column. Now the characteristic equation of that 3 by 3 matrix is lambda cubed minus 5 lambda squared plus 9 lambda minus 5 is 0, which factors as lambda minus 1, lambda squared minus 4 lambda plus 5 equals 0, which itself is seen to be an irreducible quadratic of the form lambda minus 2 squared plus 1. Therefore, it has complex conjugate roots 2 plus or minus I. Now there is one real eigenvalue of 1, then there is a pair of complex conjugate eigenvalues 2 plus or minus I. So for the real eigenvalue of 1, we just need to go ahead and find an eigenvector. So we set it up in the top row, in the second row, and in the bottom row respectively. The first and third equation give the same information. Notice in the third equation the c's cancel completely. And then if this a moves over here, they both amount to 3a plus b equals 0, or b is equal to negative 3a. So if I set a equals 1 and b equals then minus 3, I can throw that information into the middle equation. With a is equal to 1, this is negative 6. With b is equal to negative 3, this is negative 3. And you end up getting that c is equal to 3. So we found an eigenvector. A is 1, b is minus 3, c is positive 3. And this was for the eigenvalue of 1. So here is part of our general solution. Y1 is just going to be the column 1, negative 3, 3 times e to the t. And now we get to move on to the complex valued part of the problem. Hooray for us. So we set up the matrix times an unknown column is 2 plus I times that column. Row by row, we get the following 3 equations. Now this top equation is pretty convenient because it allows us to quickly solve for b. Specifically, if I subtract 4a from both sides, we get b is now negative 2 plus I times a. We're going to take this value of b and substitute it into the second equation. So we're going to add the 6a over, so here's a plus 6a. Otherwise, c is equal to 2 plus I times b, but b is negative 2 plus I times a. If you distribute all of this out and then add the 6a, it's just a. The entire complex part of this expression actually completely vanishes. So c must equal a. Meanwhile, b must equal negative 2 plus I times a. So if we set a is equal to 1, then c is equal to a, also 1, and b is negative 2 plus I times a, and there it is. So we have found an eigenvector for the complex eigenvalue of 2 plus I. We need to separate that eigenvector into its real and complex parts. So the real part is 1, negative 2, 1. The complex part is 0, 1, 0. And recall our general form, e to the alpha t, u cosine beta t minus v sine beta t, which in this case simplifies to, well, alpha is 2 and beta is 1. U is the vector 1, negative 2, 1, and v is the vector 0, 1, 0. So throwing that all down into here and simplifying gives us that our second general solution is this right here. But for the other solution generated by this same choice, we have e to the alpha t, v cosine beta t plus u sine beta t. Making all the same substitutions, we can simplify it all into this column right here. Alpha is still 2, beta is still 1, u is still this column, v is still this column. So we have now found a fundamental set of solutions. Y1 was given by this column here. Its initial conditions, if I plug in at t equals 0, give me 1, minus 3, 3. Y2 was this column here. If you go ahead and set t equals 0, it will give you this column. And Y3 with its initial conditions. Now, the general solution is a linear combination of the y1, y2, and y3 that we already found. We go ahead and plug our initial conditions into this expression. On the left, our given initial conditions was 3, minus 10, 13. But on the previous slide, we worked out the initial conditions of y1, y2, and y3 respectively. So in the top row, c1 plus c2 must equal 3. In the middle row, negative 3c1 minus 2c2 plus c3 must equal minus 10. And in the bottom row, 3c1 plus c2 plus 0c3 must equal 13. We now have 3 equations in 3 variables. We can eventually solve this as c1 must be 5, c2 must be minus 2, and c3 must be 1. And now we can take those known values of C1, C2, and C3, throw them into that expression there, replace Y1, Y2, Y3 with the column forms that we already found, and if you like, combine this all into one gigantic column. Here is our solution, Y. For our third example, find the general solution to this system of equations. Well, we know what we need to do. We need to take the characteristic polynomial and find its roots. So we're going to take a minus lambda I, subtract lambda off the diagonal, and compute a determinant. The determinant of that will be negative lambda cubed plus 20 lambda squared minus 176 lambda plus 960. We've got to factor this to find the roots. This is all familiar work, so here it is. Therefore, we have three eigenvalues, 12, and then the complex conjugate pair, 4 plus or minus 8i. Now for the real eigenvalue of 12, we just need to find an eigenvector. And again, this is duplicating a lot of the sort of work we've done before, so we're going through it quite quickly. We have two options. We can set up a times unknown equals 12 times unknown. Alternately, a minus 12i times unknown equals 0. And if we do a minus 12i, we just need to subtract 12 off the diagonal, converting this to 0, minus 22, and 6. 0, minus 22, and 6. Either way, we just need to find a non-zero solution. A possible non-zero solution is given by the column -1, -9, 15, and this generates a term of our general solution of the form -1, -9, 15, e to the 12t, and that takes care of the real eigenvalue of 12. Now for the complex conjugate pair of eigenvalues, just pick one. We're going to pick 4 plus 8i and find an eigenvector. So here we have a minus lambda I. So from our matrix A, on the diagonal, we subtract the eigenvalue. So if I subtract 4 plus 8i from each term on the diagonal, 12 goes to 8 minus 8i, -10 to -14 minus 8i, and 18 to 14 minus 8i. So here is a minus lambda times the identity times the eigenvector should be 0. With the aid of a computer algebra system, again, we're speeding through this because we've solved these sorts of things a couple times now. One possible choice for an eigenvector, A, B, C, is 5, -7 plus 4i, and 5. But we want to split this up into a real and imaginary part. So the real part is 5, -7, 5, and the imaginary part 0, 4, 0. So here we have our eigenvector for this eigenvalue split up into its real and imaginary parts. So for our complex eigenvalue of 4 plus 8i, with some work, we can find an eigenvector, split it up into its real and imaginary parts. Then we can use the formulas that we have established already. Here we have alpha is 4, beta is 8, the column vector u is the real part here, and the column vector v is the imaginary part here. Throw it into this equation, simplify everything down, eventually you'll end up with this column right here. The other solution we can generate, we just copy the formula, e to the alpha t, v cos t plus u sine beta t, end up with this column right here. Now that we have three pieces to put together, we have our fundamental set of solutions. We can state our general solution is a linear combination of them. We refer back, we just copy and paste y1, y2, and y3. There they are. We can simplify this into one gigantic matrix, and there it is. Here is our general solution to the equation given in this problem. So altogether, what did we do? Well, we're accounting for the possibility that our n by n matrix of constants has a complex conjugate pair of eigenvalues, alpha plus or minus beta I. For either one of them, find an eigenvector and split it up into its real and imaginary parts. Call this u plus vi. Then we can get a pair of linearly independent solutions to the system, y1 and y2 of these corresponding forms. It's then possible to also account for deficient complex eigenvalues. We didn't do any examples like this because it very rarely would come up in an introductory course, and we're not trying to delve too deep in these videos. But now what we can do is we can solve any first-order homogeneous system with constant coefficients.